Well, my dear participants, now I am going to fit the same data of coagulation with AOV. AOV stands for analysis of variance. So, here M1, AOV, coagulation versus diet, data is equal to coagulation. So, summary M1, it gives a different kind of summary. So, this is known as analysis of variance summary. Diet, there are 4 diets. So, degree of freedom is 4 minus 1, 3. Residuals, it is n minus 4. The total number of observations is 24 minus the 4 groups. So, it is error degree of freedom, residual degree of freedom. Then sum of square, then residual sum of square, and then mean square. You divide this by this, it is mean square, and divide this by this, it is residual sum of square, mean sum of square, and if you divide this by this, it is f value, and this is the p value. So, p value shows that we are rejecting the hypothesis that all the diets are having same effect. That is being rejected because of this p value. Then we can have table of means. So, model dot tables, the function is model dot tables, m1 underscore AOV, type is equal to means. So, here table of means, grand means, overall mean is 64. Then diet, A is having mean 61, B is having 66, C is having 68, and D is having 61, and they replicate the number of observations. A is having 4 observations, B is having 6 observations, C is having 6 observations, and D is having 8 observations. Thus, we conclude that there is significant difference in mean coagulation time for different diets. We can get a graphic summary of table of means, and the function is plot.design coagulation. See, just I would like to go into analysis of variance. So, here we have to require far away package to have the data coagulation. So, this is the data coagulation. Then table, we are generating the table of diets. Then summary coagulation. So, these are the summary of results of coagulation data. Then we are having get means for each, it is this. Then have SD for each group, and then get standard error of means for each group. So, these are the summary of results. Then plot, since this is numeric and this is, and diet is factor variable, this plot function, if both would have been numeric, it will generate scatter diagram. But here this one is numeric and this one is factor variable. So, that is why it generates box plot. So, it is the box plot. I have already discussed this box plot, I have already made the interpretation. Fitting with one-way ANOVA model, this is the one-way ANOVA. See, actually this is the implementation of LM. So, LM coag versus diet linear model, and this summary of results here, it gives the contrast of diet B versus diet A, diet C versus diet A, and diet D versus A, and these are the significant effects. So, it is more informative as compared to analysis of variance. When we make use of ANOVA, see, ANOVA output, here it shows that there is significant difference between the 4 diets. But what is the quantity of that difference? It is not shown here. Just we can compute, we make use of the function model.tables, and this is the fitted object and type is equal to means. So, we are getting means. Now, we can get summary of these means, overall mean, and so plot.design. See, this is the means of coagulation time. So, this is the overall mean, this is the mean of C, this is the mean of B, and this is the mean of D and A. They are matching. So, D and A, they have coagulation time below average, whereas B and C, they are having above average coagulation time, and C seems to be the best, followed by B in terms of coagulation time. So, this is the now single factor with more practical examples. So, just I would like to go on the PDF, and here I would like to discuss. Select single factor with more practical examples. Analysis of single factor is most common among biologists. It can also be considered as comparison of more than two groups. The two functions AOV and LM are meant for the analysis of such data. Let us start with the introduction of the data set around which all the related concepts will be discussed. Fat data, the fat data which is available in Snedeker and Cochrane's book. I have already talked about this book. It is Snedeker and Cochrane's book, Statistical Methods. On page 259 is a data frame which consists of 24 rows and 3 columns. Actually, it is not in the form of data frame, it is in the form of the table, but we have created a data frame out of this. So, how we have created data? See, fat data, expand.grid, replication, paste are 1:6. So, there are 6 replicates of each data. Then fat, see, there are 4 labels of fat, 1:4, and then fat data absorption. Actually, these are the data sets which are about absorption of the fat in different types of dough nut. So, these are the absorptions which is response. So, after creating this data, we have print fat data. So, this has been created. And then we can save this data into the using the function write.table, file is equal to fat data. So, when we will go into its source file, see, fat data, we have created fat data. So, when we print this, it is fat data. So, here we can view fat data. So, this is the fat data, replication and fats, and this is the whole data. There are 24 observations. And this is the fat type 1, fat 1, then fat 2, and then each observation, each treatment is being replicated 6 times, R1, R2, R6, R1, R2, R6, R1, R2 up to R6. So, this is the fat data. Now, we are adding a column of absorption, that this is the numeric column. So, what we have done, that in the fat data we are using a $sign. So, this will add in the fat data object, and that is absorption, and absorption response of first replicate and fat type 1. So, it is 64.72. Response of the second replicate and fat 1, it is 72. So, like that we have created. So, when we will run this command, C, and if we print fat data, we are having the columns, we can view fat data. Yes, now this column absorption has been added, and it is as per these treatment combinations. It is as per these treatment combinations. So data has been created. Now we can save this data using the function write.table. Write.table, fat data, this is the data object which has been created, and file is equal to fat data.txt. So this will be saved into a file. So this file fat data is here. This is a text file which has been there, which has been saved. Now to print the results, we have print fat data, and then statistical analysis with this data. Now I am going to talk about statistical. We have talked about these things. Now statistical analysis. The function AOV is used for the purpose of fitting the model, which is defined as absorption is equal to overall mean plus fat plus error. So this model could be fitted as M2 is equal to AOV, analysis of variance, absorption modeled as the function of fat, because this one and this one, they are not depicted in the model. So data is equal to fat data. This is the fitted object and contains a lot of information related to the analysis of one-way data. They can be printed as per the requirement. For example, to get brief summary of the results, print M2. So this is the summary of results. Summary, this is the fat has 4 levels, so it is 4 minus 1, 3. This is 20. This is sum of square, this is mean sum of square, this is F value, and this is P value. So this P value shows that there is significant difference between the average absorption of fat in dough nut in all the four fat types. So model.tables, type is equal to means SC is equal to true. So here it has grand mean, fat data, then standard error of difference of mean. So this is nothing but SED. Now multiple comparison. From the analysis of variance table, it is evident that P value is less than 0.05, resulting that on average the 4 effects differ significantly. To make a pair-wise comparison, several methods are available, but Tukey's honest significant difference has been implemented through the function TukeyHSD. So TukeyHSD, which is equal to the factor is fat, SC is equal to true. So this is Tukey's multiple comparison overall. This is fat 2 versus fat 1, the difference is 13, and lower bound and upper bound of difference is this one, and P adjusted. This shows that this difference, fat 2 versus fat 1, is not significant. Similarly, fat 3 versus fat 1 is not significant, whereas fat 2 versus fat 4 versus fat 1 is not significant, fat 3 versus fat 2 is not significant, fat 4 versus fat 2 it is significant, and fat 4 versus fat 3 it is not significant. So it is only fat 4 versus fat 2 the difference is significant. This output is self-explanatory and it is clear from the last column of p values, that fat 4 minus fat 2 is statistically significant. So fat 2 versus fat 4 versus fat 2, this contrast is only significant. Graphic view, graphic view. See, graphics are more powerful means to understand a phenomenon. Again, the kind of summary features discussed in comparing two treatments can be extended in this situation. So, standard error of mean function with fat data t apply, we are computing the mean vector, and then here we are computing the standard error of each fat label. R bind, so mean is equal to and SC is equal to, so mean, these are the means of for the fats, and these are the standard errors. To get an error plot for which reported in figure, so here BP is the bar plot, mm means means, these are the means, means. X lab is equal to fat type, Y lab is equal to observed fat in gram, main is equal to, there is no main title, and Y lim is C0 110. Then arrows, we are adding arrows, BP and then minus SC, and then BP plus SC, code is equal to 3, angle is equal to 90, and length is equal to 0.9. So these commands give this plot. This is the error bar plot. So these are the standard errors. And these are the means. So plot of means, another plot which represents the summary features reported in the function model.tables, can also be constructed here, and that is plot.design. So before that we have used plot absorption versus fat. So this gives box plot. So here the fat 4 give the least absorption, whereas fat 2 give the highest absorption, and followed by fat 3 and fat 1, they are close. So these three are closer, whereas they differ with fat 2, and that has been depicted in the analysis also. Plot.design fat data, and we are selecting the columns absorption and fat. So here at least one numeric column and one categorical column should be there. So absorption and then fat. See, fat 2 is the maximum observed, whereas fat 4 is the minimum absorption. See, fat 3 and fat 2, they are above average absorption, whereas fat 1 and fat 4, they are below average absorption. So now TukeyHSD plot, Tukey honest significant plot. Here we are giving the option par mar 3, 8, 3, 1. So these are the margins of the figure, because we expect on the here we are having in the margin 2, this is the margin 1, this is margin 2, this is margin 3, and this is margin 4. So here we expect more margins, so that's why we have set margin C 3 in the bottom, whereas 8 in the left side, in the left side, and 3 on the top and 1 in the right. And then plot TukeyHSD M2, which is equal to fat less is equal to 2. Less is equal to 2 means they are perpendicular to the axis. Less is equal to 2. And see here, this vertical line, if it is crossing some interval, that is not significant. So fat 2 versus fat 1 is not significant, because it is crossed by the vertical line at 0. Fat 3 versus fat 1, it is also not significant. Fat 4 versus fat 1, it is not significant. Fat 2 versus fat 3 versus fat 2 is also not significant, whereas fat 4 versus fat 2, it is not being crossed by the vertical line as 0. So, this fat 2 versus fat 4 versus fat 2, this contrast is significant. So, this is the interpretation of these figures. Analysis of factorial experiment. So, here analysis of factorial experiment. Factorial experiment means factors more than 2. Analysis of factorial experiment. Factorial experiment are also extremely extensively used in conducting biological experiments. Most of the pioneering work has been done in the field of designed experiment using the real data of biological and agricultural experiments. This is one of the great methodologies of statistics. See, actually I have quoted this. This is one of the great methodologies. Virtually there is a journal, Statistical Science, which publishes one review paper and 2 or 3 review papers and one interview of a leading statistician. So, in 1987, they have published an interview with C.R. Rao, and Maridu Groot asked him from C.R. Rao that what opinion you have about design of experiment and sample surveys. So, C.R. Rao tells him that these are the 2 great methodologies of statistics. Then he immediately asks the next question, what opinion you have about inference? He says if data is properly collected, properly designed, properly arranged, inference looks obvious. So, that is why I have written this is one of the great methodologies of statistics. Now, cowpea data, again a cowpea data is available with Snedeker and Cochran, 1967, page 308, in which 3 levels of variety and 3 levels of spacing are the 2 factors with 4 replicates. Response is yield, cowpea, hay, LB per 100 Morgan plot. Design of experiment is randomized block design. Details of the data is reported as. Actually, I have tried to report this format of the data because it is discussed in the book of, this kind of format is given in the book of Snedeker and Cochran. So, here variety 1, spacing 1, spacing 2, spacing 3, and then these are the replicates 1, replicate 2, replicate 3, replicate 4. So, this we can generate by using R commands from the data frame. See, creation of data frame cowpea. What we have done, cowpea is equal to expand.grid, replication is equal to paste 4, 1:4, sep is equal to this, spacing paste S 1:3, variety this is. So, when we run these things, actually we have to enter the response just like I would like to run this data, so that one can understand that how these things are being generated. See, expand.grid cowpea, it generates the design. It generates the design, and see, the first argument of expand.grid changes fast, R1, R2, R3, R4, R1, R2, R3, R4, followed by the second argument which is S1, 1, 1, 1, then S2, 2, and here variety. So, it is the least changing. So, the order of change here R1, R2, R3, here S1, 1, 1, then S2, 2, 2, but here V1, 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 V1 up to here, and then it changes like this. So, it depends upon, and then we are having the response of R1 and then S1 and then variety, and that response is 68, 50, 56. So, we have to enter as per the response of these combinations. So, we have added this, and that column is yield. So, we have done this. Copy. So we have got the data. Now yield we have entered. Now we can fit the model. We can fit the model and we can get the result. Write that table, we have saved the data as .txt and then tab 1 with copy data frame, this data frame, F table, the flat table, X tabs, yield, this is the response variable, yield versus variety, this is the first argument, plus spacing, this is the second argument, plus replication, this is the third argument. So this F table will generate a table like this. Fitting up the model, yield is equal to variety plus spacing plus variety, interaction of variety in spacing plus error. So this is equation. And we are going to write this argument as the function AOV, yield versus variety into spacing. Actually, variety into spacing here, there is the concept of formula in Wilkinson and Rogers which has been adopted here. If we write A star B, that is main effect of A plus main effect of B plus interaction effect of AB. So either you write this expanded form or we write this short form. So we have written here the short form, and that is variety into spacing and data is equal to copy. So we are getting the results. Variety, there are 3 levels of variety, so degree of freedom is 3 minus 1. Spacing 3 levels, so 3 minus 1, and then here 2 into 2 it is interaction. See, all these effects, main effect of variety is significant, main effect of spacing is also significant, and then spacing, then interaction effect of variety in spacing is also significant. Then model dot tables, means SC is equal to true. So we are having table of means, and then methods, multiple comparison, plot of means, option plot dot design. Here the column has yield, variety and spacing. So this command generates this kind of graph. So here variety and then spacing. It shows the varietal effect is much more because it has more range as compared to the spacing. So variety is having more effect on yield as compared to spacing, and this is the overall mean. This is the overall mean. So it is due to plot dot design, cow. This is the yield, variety and spacing. Then numeric summaries, mean plus minus standard error of mean, with cow p, t apply mean, standard error and round up to 3 places of decimal. So these are the means and these are the standard errors. So then summaries for spacing, see round, this is summary of spacing. Variety for summaries for interaction spacing. So these are the summaries for interaction. Then box plot, plot yield versus variety, plot spacing, data cow p. So these commands have, this is the box plot of variety. So here there is significant difference between variety 1, variety 2 and variety 3. And the box plot of spacing, here it seems to be significant effect but not as compared to here. Varietal effect is more as compared to the spacing effect, but there is significant effect. TukeyHSD, multiple comparison. Here V2 versus V1, the difference is this and it is significant. V3 versus V1, it is significant. V3 versus V2, it is significant. So TukeyHSD and then TukeyHSD spacing versus variety. And look into the graphics of TukeyHSD. So this is the graphics of TukeyHSD with variety. So there is no vertical line at 0. So that means V3 minus V2 is significant, V3 versus V1 is significant, and V2 versus V1 is also significant. Whereas here S2 versus S1 is not significant because it is being crossed by the vertical line at 0. S3 versus S2 is also not significant because it is being crossed, whereas S3 versus S1 it is not being crossed by the vertical line at 0. So that means it is S3 versus S1 is only significant. So similarly we can have these. So those interactions which are being crossed by the vertical bar at 0, they are significant interactions, remaining are not. So this is all about today's lecture about this. Completes the hypothesis testing. So in the next lecture I shall talk about some other concepts. So that's all for today's.